Good morning, my YouTube viewers. Crystal here. I wanted to make another video for you this morning because I've been hard at work pretty much all night long, and I did some more work on my anonymous training deficiency file because I had read in one of Jason Brownlee's blog posts that you can use random forest for time series analysis as well. So I decided to use random forest and some other models in addition to that, and I decided that I put all of that in a file, and it's in my GitHub account. So if you look on my GitHub account under TS Anon Training Def Bagging and Other Models, you'll find the file and you can follow along with me. So the problem statement for this is the problem statement is training deficiencies for an anonymous department in an organization have been calculated from 2016 to 2020. It's worth noting that the COVID-19 pandemic started in early 2020, and this would have an effect on the training deficiencies. So the first thing we did was we loaded our pandas and our NumPy libraries, and the next thing that we did was we loaded and read the CSV file that I created. So this CSV file has the month and the year and the training deficiency. The month and the year is actually the index. So we did it using Matplotlib, and you can see this is what the training deficiencies look like from 2016 to 2020. And then we plotted it again using a different type of plot because there were no negative values. We could plot it to where you could see it on both sides, and so we plotted it that way so you can just get a different view of the training deficiencies. The next thing we did was we defined our X and Y values. X is df.index.factorize 0, reshape -1, 1. Y is df training deficiency values. So we split our training up for training and testing using train test split. So we split it on the X and Y values. We have a test size of 0.3, random state of 0. So this one we decided to use the linear regression model. Now the linear regression model is just a straight line. So on the linear regression model we scored like a 9%, and then on the validation data set we scored like a -46%. So that's pretty poor. And on the RMS we had a 44.79. And this is the a comparison of the actual values against the predicted values. So you can see the actual values and then what the model predicted they would be. So this is one good reason to know why, we're in the middle of COVID-19 pandemic and you have a lot of people making predictions. So this is why you need to make sure that you use the correct model whenever you are making predictions, because if you don't use the correct model, then your correct predictions are going to be way off, as you can see. So we our predictions, so you can see the plots. And what we decided to do was we decided to use random forest as a model because Jason Brownlee in his blog said that we can use random forest. So we got a 95.65% accuracy on X train, Y train, and 60.35% accuracy on X val, Y val. We have an RMS of 23. And we compared our predicted values against our actual values, and you can see they are a little bit better. So we have graphed this so you can see what it looks like on a graph, and you can see that they did a pretty good job on the higher figures, but not a very good job on the lower figures. So the next thing we did was we decided that we would use Ada Boost because I've had a lot of success with Ada Boost. So I thought, well, I'll see what happens if I put this on Ada Boost. And if you don't define a estimator, then what it will do is I think it will use decision trees. So we had a 92.78% accuracy on X train, Y train, and we had a 37.36% accuracy on X val, Y val. So in this instance, Ada Boost didn't do very well. And that's why whenever you are making predictions, you have to make predictions on lots of different estimators because every estimator is going to work differently. We had an RMS of 29. And so here you can see we've got a comparison of our actual values against our predicted values. And we have a plot on the Ada Boost. So you can see that Ada Boost did pretty good on the high numbers, but it didn't do anything with the low numbers. The next thing we do is I decided I'd use bagging. I've never really used bagging before because my system always crashed. But since this was a small program, it worked without crashing. So the bagging classifier, we had a 95.65% on X train, Y train, and we had a 60.45% on X val, Y val. It was like just a tiny little bit higher than random forest, but since it was that tiny little bit higher than random forest, we have to go with the bagging regressor. And the thing is, it's like when you're entering competitions, that tiny little bit, might determine whether you win the competition or not. Had an RMS of 23.28, and then we have a comparison of our actual values against our predicted values. And we plotted it, and you can see that it did a pretty good job on the high numbers, but it wasn't very good on the low numbers. So I'm not sure exactly why it didn't pick up the low numbers, but it didn't. So now we created a lag set, and this is something that Jason Brownlee uses. And in order to get the lag set to work, I had to use the algorithm that he used. Otherwise, it wouldn't work. And we got an MSE of 317. And these are the predictions. And this is the actual values against the prediction values on the lag set. And you can see this is a graph of the lag set. And so you can see that it looks quite unusual. It just seems to me like it's steadily increasing and then it decreases. And then we tried our polynomial regression just to see what would happen when we put it on a polynomial regression with linear regression. And I could probably try polynomial regression with another model and see how well that works if I want to, such as lasso or ridge or elastinet. And we got a 57.49% accuracy on X train, Y train, and 60.43% accuracy on X val, Y val. We got a 23 on our RMS. And here's a comparison of the actual values against the predicted values. So you can see how that works out. And then we've got it charted. And it seemed like, again, it did okay on the high values, but not so well on the low values. And that tends to be the theme. We did a polynomial on the 10th degree just to see what would happen. So we had 82.6% accuracy on X train, Y train, and not very good, like a 2% accuracy on X val, Y val. We had a 36 RMS, and this is a comparison of the actual values against the predicted values, and we plotted that. And the next one, just to see what would happen, we decided we would use NumPy polyfit just so we could try to fit the dots on. And on the NumPy PolyFit, I just set it up for a 12th degree, and this is what we got when we set it up for the 12th degree. So in this particular example, just did just a tiny little bit better than the rainforest. So I couldn't go with that classifier. And that completes this presentation. If you like my video, please like, subscribe, and share. If you like the work I do, I've got my email address for my PayPal account if you want to leave a donation, because I do not have enough subscribers to monetize, and the only way I can make any money on this channel is to ask for donations. So thank you so much for watching this video. If you have any ideas and comments or thoughts, then you can put them in the comment section. And I look forward to making another video for you soon.